friends. Welcome to this Advances in Agriculture Engineering course. So, in this module, we are going to talk about the field water balance. So, basically, if we are talking about field water balance, that means we are looking at the field level basically. So, if you take a piece of land vertically down, so how the water you are applying on top is going to transform into different quantities, different components of water balance. So, if you see here, for example, so this is the field unit. So, for example, this is the field unit. So, this one the part of the field. So, this is at the top. So, the amount of water which is input to the the agricultural field, that is could be irrigation or it could be the rain as effective precipitation that is going into the soil, and then the losses could be like runoff, which is running off, the amount of water which is running off from the field. The other one could be the evapotranspiration through plants and the ground, and then the other loss is the deep percolation. So, the water uh, which is passing through the root zone is called deep percolation. So, here if you see this water balance equation, so we are focusing on the field plot. So, the precipitation, irrigation, so these are the inputs. So, then the runoff, depercolation, evapotranspiration or evaporation, or the losses. Then if you see this soil water, this is the amount of water which is present in the soil in the beginning, and so this is it is in the final, and the soil water in the beginning. So, this is also the input. So, this is already some water is present in the soil. So, that is input, and then the end of the water which is end of the time or end of the day, the water which is present in the soil, that is soil water F. So, UW, this is upward flow which could be the input to the system from the groundwater. So, altogether these are the total inputs, these are the total inputs and the total outputs. So, it should be balanced basically. So, that is the objective of this. The water balance is very important in order to find out different water balancing components, and then this is very important for field water management. So, unless you know how much water is is going through runoff or depercolation, right. So, that we can understand. So, carefully we have to apply in the field. So, that is the main aim of this. So, water balance is very important. So, next is, so once you know the water balance components, so how to measure individual water balancing components. For example, in this equation, if you see the first, if you see this is the precipitation. So, how to measure precipitation? There are basically through rain gauges. So, it could be like Simon's rain gauge, so which is a simple rain gauge, like it is a simple collection, the tank or the collection bottle. So, which has a conical collection at the top, and then the bottom is the cylinder. So, it collects the the total, the cumulative rainfall in a day. So, this one, and then we have a floating type rain gauge. So, floating type rain gauge contains a drum wounded with a graph sheet, and then there is a float down here, and the float there is a pen which is attached to the float. So, depends on the water which is accumulating inside every time. So, the float is going to rise, right, rise, and then accordingly the pen is going to draw the water levels, but the drum will be moving, like a drum is attached to a clock basically. So, the clock will be moving. So, accordingly you will be knowing at what time the depth of rainfall is collected. So, that will be known. And then the third type is the tipping bucket. So, in this the number of ticks or tips made by a small tiny bucket here. If you see, there are two buckets. So, one bucket here, another bucket here. So, first one bucket is positioned to the bottom. So, once it is filled, so generally the volume is 0.25 mm. So, once it is filled, so due to gravity or weight of the bucket, this bucket going to go down, then this will go up. So, that way it is going to make a tip here, then similarly the other tip here. So, it is like simultaneously the tips will be taking place during the storm event. So, number of tips will be counted by the instrument. So, because each tip equals to 0.25 mm, accordingly it calculates the total rainfall and also it gives the instantaneous. So, rainfall rate as well as, or that means rainfall intensity as well as the total rainfall will be calculated using the tipping bucket type rain gauge. There is a simple rain gauge, the form rain gauge. It contains the transparent the cylinder, and then the top there is a collector. So, this is already calibrated. So, there are measuring marks. So, this will be attached to a fence and then so the amount of water which is collected will be clearly seen through this marks. So, these are measurements and this will be recorded accordingly. So, the next is here in more details of tipping bucket type. If you see here, as I said, this consists of pair of buckets and a funnel. So, pair of buckets are here, one bucket and second bucket. The volume of or the depth of each bucket can collect will be equal to 0.25 mm of precipitation. So, if the tips discharge rainfall into the container, bringing the other bucket under the funnel. So, it is like alternatively one bucket will go down, other bucket will go up. So, here there is a sample rainfall calculations. So, these are the tips on this side and the rainfall on the other side, since it is calibrated. So, for example, suppose for this reading, so since it is 0.25, that multiplied by 10, so that will be 2.5 mm rainfall you will get. So, the next is okay. Yeah, here you can see clearly the graphics how particular bucket is filled and then other buckets will be emptying. So, it is like, so this way when the bucket hits down there is a tip, okay. And now measuring the irrigation water, this is the second water balance component. So, the irrigation water here let us say I. So, generally if this is a pipe flow, we will be using flow meters and on the field on site. So, this is the furrow field, this is the furrow irrigated field. So, in this field, so each furrow needs to be irrigated. So, we should be knowing how much how much is the discharge to each furrow. So, that will be calculated using bucket and stopwatch. So, stopwatch will be set and then the bucket will be filled for a particular time interval, and then the volume collected in the bucket for that duration will be taken as volume of volume. So, that will be the discharge. So, volume divided by time will give the discharge. and this is the partial flume. So, partial flumes are used if there is channels like irrigation channels. So, you will be knowing how much water really releasing to the particular field using the partial flumes. And then the next is runoff. So, runoff will be measured either using flumes or using some special kind of samplers, that is ISCO samplers. If you see in this picture, the flumes or basically or auto samplers, they work, the discharge will be estimated based on the area velocity method. So, this is the trapezoidal shape, knowing the depth and velocity. So, velocity in this case will be calibrated, it is already calibrated using pressure transducers here, right. So, the basically the level, so the depth as well as the velocity will be collected, and based on the shape, I mean designed shape. So, that will give the discharge. So, q is equal to A into the velocity. So, where A will be taken from the shape and the depth of flow, and velocity will be measured with this sensor, that is velocity recorder, flow velocity meter. Okay, so here there is a special kind of the ISCO sampler. ISCO sampler also works on the same principle. So, here the runoff will be collected or through a pipe, so pipe kind of thing. So, we will be knowing the pipe dimensions, and then there is a sensor, the velocity and as well as a depth sensor. So, that will give the velocity and depth, and correspondingly discharge will be calculated. The special I mean provision here we have is, so if you go to the next slide. So, there, so this is ISCO sampler. So, ISCO sampler has different samplers inside to collect the sediment samples, the bottles. So, it can go like sequential samples or composite samples. So, you see here, this is the furrow irrigation collection point and flow going from top to bottom. This is the ditch. So, the ditch will collect runoff from all furrows and throwing through a pipe, and from there the ISCO sampler is going to measure the flow velocity, and also based on the based on the programming instructions or programming instructions. So, it is going to collect whether the sequential sediment samples or composite sediment samples or runoff samples are to be collected. So, and here this graph shows this side is the temperature and this side is the runoff. Anyway, this is not our I mean focus area, but basically the runoff I mean on the time on x axis. So, a particular time, what is the runoff we measured through ISCO sample is given here. Okay, so, this is just an example. And then evapotranspiration, the other component is the evapotranspiration, that is ET. So, it has both evaporation and transpiration components. So, evaporation basically occurs all moisture wet surfaces, that could be the plant or soil or including like plant, water or soil, and the transpiration basically through plant body, and there are some specialized openings called the stomata. So, the water transmits through stomata. So, the amount of water which is passed through the stomata is called transpiration. So, in this case the evapotranspiration in case of I mean crops. So, it has both water on the surface in the plant body. So, that will be evapotranspiration. So, both evaporation and transpiration occurs in response to a climate demand. So, basically what happened, the climate, if you see here, E is equal E plus Et is equal to E plus T. So, transpiration basically is taking place through plant body, whereas evaporation either through through the plant surface or the soil surface, okay, or if there is a water body, there is a water surface. Okay, so these things is going to happen. But this is all happening due to climate demand. So, the climate demand depends on the solar radiation, temperature, humidity, wind speed, and all other parameters. The terminologies for ET includes like the potential. The first one is potential evapotranspiration. So, this is the maximum rate at which the water is removed from the plant, from the crop area is called potential evapotranspiration, basically under no stress condition. So, the crop is well grown without having any water stress and nutrient stress. So, that is potential evapotranspiration. Whereas, actual evapotranspiration, so he is the transpiration from a crop area, but the crop may be under stress condition. So, under the stress condition we expect. So, reference crop evapotranspiration, that is basically this is the rate of evapotranspiration from an extensive surface of 8 to 15 centimeter tall, mostly the green grass, and which is uniformly grown over an area, and completely that should be completely cover the whole land, right, completely shading the ground, and not short of water. Okay, so these are the main conditions for reference crop evapotranspiration, and it is denoted with ET0. So, this is very important because in order to estimate evapotranspiration, ET0 needs to be estimated. So, let us go to the how to estimate the evapotranspiration. So, there are direct measurements of ET. For example, in this case, so field measurement, so field water balance equations, what we have talked, same equation can be used knowing the other water balance components except evapotranspiration. For example, here our interest is to find out evapotranspiration. So, this is the soil moisture, the reserve or the difference in soil moisture. So, irrigation water, effective rainfall, upward flux, this is downward flux, we can say D, and surface runoff. So, knowing all the parameters you can estimate evapotranspiration, whereas soil moisture can be estimated using the volumetric moisture content multiplied by the the density and then root zone depth. So, this is the direct measurement of ET or direct estimation of ET from the volume balance equation. And then the next is measuring by lysimeters. So, if you see here, for this we need 3 lysimeters. One is bottom closed, the other 2 are bottom opened. So, in one of the bottom opened will be growing plant. So, 3 this set of lysimeters are installed in the field, and will be observing the daily water water levels basically. So, this idea is for rice crop. So, ponding water will be measured daily. So, for example, A is the ponding water. So, the difference in ponding water levels like day 1 and day 2 in case of A will give the evaporation basically. So, because there is no other loss except evaporation here. In the second case, in B case, the difference in ponding depth will be the evaporation plus depercolation. So, these two. Okay. So, now if you can differentiate these two, like in order to get evaporation, so what you have to do? You have to do B minus A, you get the evaporation. In the third case, so the difference in ponding depth will be equal to evapotranspiration and depercolation. So, these are the two losses. So, now the evapotranspiration will be estimated using the C, that is the difference in water level, minus B minus A. So, you will get the evapotranspiration. This is simple math. Only thing is installing these lysimeters in the field and finding out the water levels. And then the direct measurements of ET, there is another way of estimating measuring ET is using pan evapometer. So, class A pan evapometer will be installed in the field. So, you will be knowing daily loss. So, the loss in water level. So, the pan evapometer, like it is raised at the height of 15 centimeter from the ground, and it contains a pan of 120.7 centimeter diameter and 25 centimeter depth, and then at the corner there will be stilling well. So, the stilling well is useful to take measurements, because when you take measurements here, then there will be a fluctuation. So, stilling well means, so the name indicates stilling well means the water level will be stable here. Okay. So, there is a recommendation that we will be keeping up to 5 to 7.5 centimeter from the rim. The water level will be filled every day. So, early morning around 8 a.m. you come to the field and note down the reading, or you replace the amount of water which to this level, so that the replaced amount will be equal to the loss of the that's evaporation in the previous day. So, that is E pan, and there if you can multiply with the pan coefficient, that will be ET0. So, reference evapotranspiration. So, knowing this, and you can multiply with the crop coefficient, you get the evapotranspiration. So, that is another way of doing evapotranspiration. Now, there is indirect methods. So, indirect methods, just as I mentioned, so it contains, we will be using mostly the reference evapotranspiration and multiplying with a Kc value. So, here in this case, if you see the picture, if it is the reference crop, so and then climatic factors, so you whatever evapotranspiration you observe, that will be reference evapotranspiration. This is a grass reference crop. So, that means 8 to 15 centimeter tall, and it is completely covered the ground, and no shadow in the ground, and well watered. Okay. So, in that case, and also uniformly grown over this area. So, this is ET0 will be observed. Then in the actual crop case, you have ET0 multiplied by Kc factor, that is the crop coefficient factor. So, that will be ETC. Then there is a ETC adjusted, because the stress could be not only the crop water, but also soil water. So, Ks is kind of soil water stress coefficient, and Kc. So, whatever ETC ET0 you are getting, ET0 multiplied by Ks and Kc, you get ETC adjusted. Okay. So, that is what here. So, in this way you can estimate ETC using these methods like Kc and Ks coefficients as well as ET0. So, how do you find out ET0? So, in one method is using pan method, just in the previous slide I explained, and the other method is using, there are several equations. One of those equations is FAO-Penman-Monteith equation. So, this is the Penman-Monteith equation. This is a very famous equation and most accurate estimation method for ET0. So, this is a combination method, like that means radiation as well as temperature and evaporation methods. So, or humidity methods. If you see here, there is a radiation terms, there is a this wind velocity and vapor pressure difference and the temperature. Okay, so and it contains, I think that is why this is called combination method. So knowing ET0, you can multiply it with crop coefficient and soil moisture coefficient, soil moisture stress coefficient, and then you get the ETC as I explained before. And then so here this graph as well as the plot, the figure, so the figure and the table which gives you the crop coefficient values for different crops. For example, if you see the wheat crop, okay, so the Kc initial value and mid value and Kc end value. So this table is given by FAO, Food and Agricultural Organization, FAO. So if you see here Kc on y axis and crop growth stages on x axis. So in the initial stage, this is Kc initial. In the crop development stage, so the Kc is going to rise, and mid stage again it kept constant, then and then the late season and Kc is going to be down. So this is during the season. So Kc value will vary with the season, I mean within the season based on the crop growth stage. So the next is soil moisture measurement. So other thing is soil moisture measurement. If you see in the equation, so this is the final and this is the initial. So the most basic method what we follow is the gravimetric method. In this, first we are going first we are going to scrap the land, and then you are going to shovel it, get the soil and collect the soil in a container. Then after that, the soil will be soil along with the container, or container along the soil will be taken to the to the laboratory, and there we are going to dry the container and soil at 100 degrees Celsius for 24 hours. So then you are going to first you are going to have the initial moisture reading this wet moisture, then after that you will have the dry and divided by wet. So this is the wet soil weight, dry soil weight. This is after 24 hours you take the sample out and find out the dry weight of the soil, and then the wet soil weight. So this will give the moisture content in weight basis, and in order to find out the moisture content in volume basis, you have to multiply it with the specific gravity of water. So and sorry, the bulk density of the bulk density, you have to multiply with the bulk density of soil. Okay, so the next is so next is the soil moisture measurement. Directly you can the other methods include the time domain reflectometry. So in this the high frequency pulse is going to send to the soil through these two prongs, and then the signal will be reflecting back to the reader. Then the reader is going to find out the distance is traveled, okay, and then we know the time traveled by the the signal. So knowing these two things, we will be finding out the dielectric constant. So dielectric constant will be directly related to the soil moisture. So that's why time domain reflectometry will tell you the amount of water or soil moisture present in the soil based on the dielectric constant of the media, the soil here, and the electric resistance blocks here. So this will measure the potential of the soil. So the mostly these are the porous materials. So, it could be like gypsum blocks. So that will be connected to the meter. So it will measure the soil potential, and similarly here this will measure this soil potential. this is the tensiometer which measures the soil potential. In the bottom we have the ceramic cup, and the top it is completely closed, and this is the pressure gauge. So, initially the reservoir will be filled with water completely, and then it is installed in the field on the soil. So, after a few hours, this will be coming to the equilibrium with the soil moisture. So then there will be, so suppose the soil is dry, so the water present in the tensiometer will be slowly released to the soil through the pore space of the porous cup, and then the water level will be coming down here, and that means since there is not atmosphere pressure is not involved on top, so there will be vacuum will be created. So that vacuum will be measured in this gauge. So this way it works. So that will be equal to the soil water potential. And then since the soil water potential, so we have to have the soil moisture characteristic curve in order to find the soil potential to. So this is suppose theta and psi. So knowing the soil water potential, so you will be knowing the, suppose you have a curve like this, so you will be knowing the theta here. And then the next is next component is deep percolation. So in this equation, if you see, so this is the deep percolation. So using, you can also use the water balance equation just like evapotranspiration. So knowing these components, and knowing the other components, you will be estimating deep percolation. Otherwise, you also have the lysimeter setup. So where there are 3 lysimeters, one is closed bottom, the other one is 2 open bottoms. You have a plant here, and then the deep percolation here 1 and 2. So B minus A will give the the deep percolation amount. Then the third, so this one. So another terminology, crop water requirement. So this is similar to evapotranspiration. So crop water requirement, mostly we look at the seasonal crop water requirement. So how much water really crop requires during the season, and the crop water requirement, basically it varies with the time and space as the ET demand varies with the local climate conditions. So as I explained in the initial slides, see the evapotranspiration is going, it's a climate demand. So the climate demand depends on the the space as well as time. So definitely the crop water requirement will be different in a particular area and also in a time. And then irrigation scheduling. So how we are going to use the water balance equation in scheduling and irrigation. So here if you see, the main objective of the irrigation scheduling is to maximize the yield and irrigation effectiveness. So maximize the yield and also the efficiency of irrigation system. So basically here we are giving water exactly what crop is required. So that is the main thing. All we are going to replenish the soil moisture based on our threshold. So 3 questions here. The first one is when to irrigate, how much to irrigate, and how to irrigate. So in scheduling we need to consider these 3 questions. So when to irrigate indicates that the time, and how much to irrigate, that is the volume or the discharge, the amount of water, and how to irrigate, its applicator. So which irrigation method you need to use in order to supply the required amount of water for the plant. So this, in the next module we are going to cover what are the application methods we have to irrigate the field, we will be using to irrigate the field. So for example, here using water balance technique, how to estimate or when to give irrigation and how much to give irrigation. So, similar soil moisture indicator methods. So, instead of measuring soil water content, it is computing using, so theta I minus 1 minus Et minus Pe. This is effective precipitation, that means water which is going into the soil, and this is the root zone depth. So, this one is theta I minus 1 the previous day, right, and then the previous day's moisture content minus the previous days, I mean ET and effective precipitation and depercolation. So, that will give the what is the current soil moisture content. Okay. So, is the soil water content the percent volume. So, the amount, I mean all terms are defined here. So, knowing this theta I, so this kind of water budgeting. So, knowing the previous day's moisture content, we are going to estimate current day moisture soil moisture content, knowing the effective precipitation, irrigation, and the evapotranspiration and depercolation. So, similarly, in the next day will be second day we will be using the day 1 soil moisture content and the corresponding on the same days precipitation, irrigation and other things. So, like that, this is the bookkeeping method. So, knowing one day's moisture content, we are going to estimate next day's moisture content. So, different methods of irrigation schedulings, I am not going into the details. So, you can go through this table for reference. So, there are different methods here: hand feel method, gravimetric moisture sample method, tensiometers, electrical resistance blocks, water budget approach, and modified atmometers. So, all these methods can be used to schedule an irrigation, and there are advantages and disadvantages are given. So, you can this is the best table to get an overall view of the different irrigation scheduling methods here. Let us go to a problem on irrigation scheduling. So, this problem will illustrate using water budget technique and determine when to give irrigation to a crop. So, let us say these data are given. So, daily ET and effective precipitation, this is from the table. So, this is the daily date is given July 1st, 2nd, 3rd, 4th up to 8th, and evapotranspiration, the daily evapotranspiration is given, and effective precipitation. So, that is the amount which is which is applied to the soil or taken by the soil, let us say. So, soil water content in the morning July is 23%. So, July 1st, in the July 1st they have determined the soil moisture, that is 23%, and this is by volume, this is 14%. Okay, so volume basis it is 14%. So, what you have to find out is date of next irrigation and amount if the application efficiency is 80%. Okay. So, this is the question. So, if you can understand this, so we have daily ET data, daily PE data, that is rainfall data, let us say effective rainfall data, and initial soil moisture we have. So, based on that you have to find out what is when to give the next irrigation, how much to give the irrigation. So, here there is a calculations, if you go through the solution. So, the first day 1 we use the volume balance equation theta I current day. So, theta I minus 1 minus 100 ET minus PE by DRC. So, this is previous one. So, 23% was the first day, minus 100 into corresponding days 33. If you see the first day 0.33 and PE is 0, and 24 centimeter is the DRZ. Okay. So, that is PE, and if you can do calculations. So, this will be 21.63% at the end of first day, okay, at the end of the first day. So, similarly use this for the second day. For the second day you get 20.51, at the end of second day you get 20.51, at the end of third day 19.43. So, like that this goes, but if you see we are targeting for 14%, we are targeting for 14% moisture content. So, here 13.8% moisture content you will achieve the day I mean July 8th, you will be having the soil moisture will be having 14%. So, here the amount, so July 8th is the date of irrigation. So, the next question is how much you need to give irrigation. Amount of water applied to the field will be estimated using this equation, that is root zone depth, field capacity minus soil moisture on that day, I mean previous day of irrigation, and application efficiency. So, if you see 24 centimeter is that, and sorry, this is inches, probably 24 inches, okay. And then 26 is the field capacity for 26 percentage, and we have the previous day 15.05, that is a 15 day 15.05 divided by 80% is application efficiency, and you get 3.29 inches of irrigation water you need to apply on in the morning of July 8th. So, this way we need to estimate the time of irrigation as well as amount of water required for the irrigation. So, thank you all for this I mean water balance, field water balance lecture. So, next module we are going to talk about the soil erosion and then conservation measures. Thank you so much.